Kali anak itu sih kita dia sebarang dia.
Welcome, sir.
Yeah, I apologize for
No,
the. I'm sorry, but
no.
hopefully we'll make up the lost time.
Okay, sir. You can start. Okay. Good
Yeah.
afternoon, all. Yes, sir. Session, sir. You can start the session, sir.
Okay, let me share my screen and then we can get started.
Okay, sir. Yeah, it looks there. Yes, sir. It's visible, sir.
Okay, great. Good afternoon, everyone. I hope you had a good break. What we plan on doing this afternoon session is we are going to do a little bit of coding. I'm going to talk a little bit about one application of AI. This is the image detection problem. Early this morning, what I did was I gave an overview of ML methods. And I talked about supervised learning and unsupervised learning and reinforcement learning as three big paradigms in machine learning. And in supervised learning, we talked about classification problems and regression problems. Classification problems are those where you take a data point and you try to classify it into one of few digital classes. So an example was loan was approved or loan was rejected. Um, Another example is a boss. You're running an algorithm. A company is running an algorithm in the HR department, and the HR department is making a decision on is should this employee get a bonus or not. So those kinds of where the expected output is digital, those are called classification problems. We also talked about the other type, which is regression problem. In regression problem, what the algorithm gives as an output is a numerical value. So instead of asking the question of should this person be given a bonus or not, you ask the question of how much bonus should be given. So in which case the algorithm gives a number, a numerical value. When you train an algorithm to give a numerical value, those are called as regression problems. The examples that I touched upon in the morning session were all examples which related with structured data. What is a structured data? Structured data is a data set that you can ultimately represent on an Excel spreadsheet. So there are numbers that are there in rows and columns. So that kind of data is called as structured data. I might say that, well over 90% of business problems require you to analyze structured data. If you want to try and predict stock prices, you would put in numbers related to profitability of a company, how much debt they have, what is the growth of revenue, what is the current rate of interest that they are paying, all kind of information. You would put it in an Excel sheet and you would have a machine learning algorithm analyze that. On the other hand, there are important problems that more recently we are able to tackle which don't fall into this particular category of structured data. One example of an unstructured data problem is an image detection problem, where an image is shown. This is not a data that is there that can be put in a structured set. And you are expecting the computer to be able to answer the question on, is the image that example it's a junk or not junk. And those kinds of problems are unstructured problems, unstructured data problems, right? So typically image recognition, extracting meaning from text, or text prediction, where you are expecting the algorithm to output not a number, but actually a sentence, right? That's what you expect when you ask a question with Google on your phone. With your voice, you are going to ask a question. And so the Google is actually expected to take your voice and convert that in some way to numbers and solve this ML problem to understand what you're asking, and give in turn an output that is also as a sentence, not as a number, right? Those are all unstructured data problems. And unstructured data problems are necessarily harder to think about and harder to solve, right? Be that as it may, that is an example that we are going to be talking about this afternoon. I'm going to be talking about this unstructured data problem, which is the image detection problem, right? So let me start by thinking about this, right? We kids, humans, even when the babies get to even a year or 2 years, they are very easily able to look at an animal and tell if this animal that they are seeing is a cat or a dog. But it's very hard for us to figure out how to explain how the baby is actually telling whether this is a cat or a dog. This morning we touched upon this lightly. If you had to come up with rules as to how you determine whether a picture is a cat or a dog, you might very naively start by saying, a cat is something that has got an eye, it's got 2 eyes, it's got a nose, and it's got whiskers. But the picture of a dog that you're seeing over here also has whiskers. It's got 2 eyes and a nose. So that alone is not how you define a rule. There is something else that seems to trigger in our brain, and we are able to very naturally understand that the image that we are seeing in front of us is actually a cat on the left and a dog on the right. Right? And the best way to try and solve this, therefore, is not by trying to specify rules manually, not the rules-based approach, but instead have an algorithm automatically figure out patterns and try to learn from the patterns whether the picture it's seeing is a cat or a dog. So in order to do that, we first need to train the algorithm. How exactly will the algorithm internally do it, internally learn? All of those are details which are well beyond the scope of this session, right? What I want you to do is I just want you to walk over the kind of steps that are, as a practitioner, you would do in order to try and build an image detection problem. We will accomplish something quite remarkable by the end of this session today. Even though the session is only an hour and a half, you will see the amount of development that has come about that has made it very accessible to a practitioner by very easily downloading simple code and be able to execute and actually be able to solve useful business problems from these freely downloadable code. And that is the goal of the session, therefore, is to just to give you a sense of how this is typically done. And I will share the code and data set for you at the end of the day today so that you get to practice all of this on your own as well. Okay. Now, the first thing to do in order to be able to build an image recognition algorithm is we need to provide samples to the computer. We need to be able to provide really hundreds of thousands of data, hundreds of thousands of images. And these images need to be carefully labeled. And you say that this image that you're seeing belongs to this category. And we provide these thousands of images to a machine learning algorithm, and that algorithm hopefully will learn its own set of patterns. The pattern might be different than what we as humans are seeing, but its patterns as it is, and hopefully it will learn something that's useful, right? So let us, but in order to do this, you first need access to images. Now, this problem was widely recognized that it's an important problem to solve, and we need access to images that are labeled. Now, what a professor in Stanford did is they wrote an algorithm to go ahead and download data from the web, from Google, right? And they actually employed people to sit and label these images as to what exactly does this label image represent, right? And they actually labeled well over 14 million images. And these images were labeled, you're seeing all kinds of images over here. There's an ultra marathon that is happening over there. There is a billiards game that's happening over there, and there are different sports activities that are happening. Each one of these images was labeled by a human being. And then once these labeled images were there, they actually started a competition. This competition is called as Imagenet challenge. And the part of the challenge is this: they gave 1 million images, okay, as a training set. They gave this image put this image in a public place. This image each had over 1,000 categories. So categories as wide as not just bird, cat, and horse racing. There were categories such as, this is kingfisher bird, this is a common sparrow, and this is a Persian cat, and this is a Cheshire cat, right? So they even put in all kinds of details on exactly what was that image about. And the challenge was this: you take this million images, you feed it into a computer algorithm, you write whatever algorithm you want, okay, and it can be as complex as you want, and you feed in this million images and to the computer algorithm, and for each one of these million images you tell exactly what class this belongs to, whether this is a Cheshire cat, or whether it's a horse racing picture, or it's a whitewater kayaking. You feed that image with the label. Let the algorithm go ahead and learn it, and then we have separately kept around 20,000 images which the algorithm hasn't seen till now. And then we are going to ask the algorithm to try and identify these 20,000 images. If the algorithm can correctly identify that images, we will first write out the error rate of the algorithm. What are the percentage of images that it has not been able to correctly identify? Whichever algorithm has the lowest error rate is declared a winner of the challenge, right? This is the idea of the Imagenet challenge, right? And it was recognized that this is having such a large data set is going to help the computer vision growth, right? Computer vision is an important area. We know it's absolutely essential if you have any hopes of developing self-driving cars, or for that matter, if you want to have algorithms identify radiology images and decide whether there's a tumor there or not, or if you want to have something much more commonly used, if you want to actually do an image search on Google, you want Google to be able to look through images and identify what does this particular image represent, and therefore give us the correct image. So for all of this, image identification is absolutely necessary, right? So all of this comes under the domain of computer vision. But the way people were handling computer vision before was they were actually trying to manually create rules, right? And you were coding up algorithms which used the manually created rules to try and guess what was the image that they are actually seeing is. And that was the state of affair, or when the Imagenet challenge started, right? Imagenet challenge. The name of the challenge is this: Imagenet Large Scale Visual Recognition Challenge, right? ILSVRC. Now, the purpose of this is that there were well over 1,000 categories of images that were available, million images altogether. So approximately 1,000 each, 1,000 image in each category. And they were, it was not just looking at bird or a cat or a dog. It was going into details, as this is a flamingo, right? This is a quail. This is an Egyptian cat. This is a Siamese cat. And this is a tabby cat, and so on. I don't know about you guys, but there is no way I can tell what is an Egyptian cat versus a Persian cat. I just don't have that capability. But this challenge required algorithm to be able to identify what specific type of cat it is, right? Not just that it's a cat. You are a winner only when you actually even specifically correctly recognize what type of cat it is. Now, the state of the affair when our story starts was this in 2011, not too far, right? We are just talking 9 years ago. The state of the affair at that time was this: an expert human being will be able to recognize these images with less than 5% error rate. Okay. When I'm talking about 5% error, I'm saying that it would be considered an error if I tell the wrong category of cat as well, right? So I want the expert human also to correctly tell what type of cat that person is seeing, right? So an expert human was able to identify these images with an error rate of about 5%. On the other hand, a less skilled human, not an expert person, would recognize at 10%, right? Now, the machine, the best algorithms at that time could get an error rate of about 30%. Not better than that, just 30%, right? This was the state of affair in 2011, right? Not too long back. Then in 2012, something remarkable happened. There was this team of players. Alex is one of the researchers who was part of a group from Toronto. The head of the group was this gentleman called group. During this competition, the error that was there in these VisualNet challenge was coming down by a few percent at a time. So it was moving down from 35% to 33% to 30% and so on. Every year it was moving down by a couple of percent. AlexNet came and suddenly dramatically the error dropped to 15%. In fact, the drop is considered so shocking that people actually thought these guys cheated and they had access to the test images, the unseen images, right? The thing is, you can tweak your algorithm so that next time your algorithm sees the exact same image, it will correctly tell me what it is, right? All it has to do is remember that picture and correctly tell what it is. That is easy enough to make it do. But if I show a new image, will it then correctly be able to say that it's the same thing? Correctly able to identify that? That is a big question, right? And when AlexNet dropped the error from 30% to 15%, that was just a complete surprise, right? And the beauty of this is this: AlexNet did not explicitly code in rules. Instead, they used an algorithm called convolutional neural network. Okay, forget about the initial part of the statement of convolutional. the only part that I want you to remember is neural network. They used a neural network algorithm to train the algorithm to learn automatically what are the patterns which identify a Cheshire cat, what are the patterns that uniquely identify a kayaking picture, and what are the patterns that uniquely identify a bus traveling on the road, right? If a human being had to create rules for each one of this, that's a very difficult task, and most likely that is not a scalable task. What AlexNet was able to do is they designed a convolutional neural network, a very large convolutional neural network, which was able to learn these patterns effectively and therefore reduce the error rate from 30% to around 15%. The algorithm was so complicated that they couldn't even run it on a single machine. They had to put it on two different machines. So the number of the entire network had to be split on two separate machines, and the network was trained separately. And finally, the results were joined in later on. This was state of the affair in 2012. 2013, however, now the nice thing is AlexNet, what these guys do, once the competition was won, they actually gave the source code of the algorithm out in the public. They published a paper and told how exactly they did it. Not only did they do that, they went ahead and set up a company, private company on their own. This student, Alex, even before he finished his PhD, Google had set up a company. This guy, they set up this company. Google went ahead and bought that company, and they, within a span of 6 months, Google incorporated this algorithm that these guys had figured out into Google's own image searches. Anyone who has been using Google would have noticed, expert users, I suppose, would have noticed the quality of image searches that was happening at Google algorithms dramatically improved between the year of 2012 and 2014. This is because Google went ahead and bought the company that Alex and Jeffrey Hinton set up, and they incorporated that internally into their image search algorithm. Now, since AlexNet's results were published, other people were able to copy this. And what happened in 2013 was a bunch of people from New York University were able to take AlexNet's idea, just use much more powerful hardware. And they were able to extend the size of the algorithm even more, and were able to therefore reduce the error rate even more than what AlexNet did. So from 15%, they were actually able to drop it down to around 11%. And from that point on, every single year, what happened was each company, each team used to try and find as large a computing resources that they can find, and try to work on an algorithm that create a version of an algorithm that's even more complicated than earlier, and keep trying to improve. The following year, Google themselves created one algorithm, and which dropped the error from 11.2% all the way to 6.7%. This particular thing happened in the year 2014. 2014, I don't know if you guys know, there was this movie that was released called Inception. I mentioned in the morning session itself, I'm a big movie fan. Inception was a movie that was released. It had this notion of a dream within a dream within a dream. These guys created a net, had created a convolution net, which was sort of inspired from that. It had a network inside a network inside a network kind of idea that was there. Different layers were there in the network. And so they called their network as Inception Net. The beauty of Inception Net is now you're at an error of 6.7%. So you have already beaten a less skilled human being, right? A computer is able to recognize images better than a less skilled human being. Following year, however, Microsoft did not want to get left behind in the challenge, and they took Google's ideas and the prior ideas and mixed all of them to come up with an algorithm called ResNet, which had reached a level of 3.6%. And now the Imagenet image recognition algorithms are able to do much better than what a human can do. the most amazing thing about this order of development is that each one of these companies who are developing these sophisticated algorithms, they actually left it in open source. So you and I can actually download these algorithms and then use these algorithms to build our own application to accomplish our business task, right? And this is just shocking, right? Because you're talking about Google and Microsoft. These are companies which try to make money, and the business as a whole exists in order to make money. Microsoft makes money by selling its products, right? And here was the state-of-the-art research work that they left in the public domain. And you and I can go ahead and download this model and use this model to build our own application. And in fact, we can sell that application as our own product, and without even having to declare to Microsoft or Google that we are selling a product that was created from theirs, right? And that's just amazing, right? And this is the reason why data science has come up, because it's amazing the amount of collaboration that has happened within companies where they are allowing this kind of access to cutting edge research, really. Now, I haven't talked about how exactly these algorithms work, right? And I'm not going to talk about it either. Instead, I'm just going to give you a picture in broad strokes. So what we are going to do in today's session is we are going to use ResNet, this prize-winning algorithm by Microsoft. We are going to download it, and we are going to do an image recognition task as a part of this hands-on. But before we get there, I want to give a very brief introduction of what are neural networks and how exactly do they look. And we'll see how we can use them in order to build. Okay. I promised in the morning that I will pause in the afternoon session to take some questions. So let me pause for 2 minutes and see if there is any questions.
Participants, you can post your queries in the chat window.
Okay, nothing, I don't see anything yet. That's fine, it's good. Let's go ahead and get back into the presentation again.
Okay, sir.
Yeah. So the first question that we are going to look at is how do animals recognize images in the first place? And how do humans recognize, right? Now, it's very difficult to do experiments actually digging into human brain. And, fortunately or unfortunately, I suppose that there are less restrictions on doing animal research. But Hubel and Wiesel were two neurophysiologists who did these experiments several decades ago, actually, where they inserted some electrodes in cat brain, in the visual cortex area of a cat brain. And the thing is, in case you are feeling grossed out about hearing this, electrodes being inserted in cat brains, this is fairly painless procedure for the animals, because strangely enough, although our sense of pain comes because our brain is recognizing the pain, that neurons from our, when we cut our fingers, you're sharpening a pencil or you're cutting something and you have a cut in your finger, you feel a sense of pain, and this pain is because these nerve endings from your finger send the signal to your brain, and your brain recognizes this signal as pain. On the other hand, there are no pain detecting neurons inside your brain per se, right? So which is why they can actually do brain surgery while keeping you awake, right? And this is the way many times brain surgeries are done, particularly when you are removing tumor from sensitive areas. They actually keep the patient not in the unconscious mode, but in a conscious mode. They give pain medication, they give to local anesthesia so that the patient does not feel the pain when they are opening up the skull per se. But once they are inside the skull, the brain itself does not have any pain receptors. So anyway, these neurophysiologists, they were able to insert electrodes into a cat's brain, and they were able to observe the electrical signals that were coming out as the different pictures was shown to the cat. What they realized was that some set of neurons in the brain responded when it saw straight line pictures, and other sets of neurons responded when you saw tilted line pictures. Another set of neurons responded when you saw moving lines pictures, and so on and so forth. So essentially what they realized were, in our brain, in the visual cortex, there are some what we call as low level cells which recognize simple patterns such as straight line, angle line, or moving line, things like that. Signals from those simple cells are sent to the next layer of complex cells, which combine together multiple straight lines and are now able to identify what is a square, what is a rectangle, what is a triangle, and what is a sphere, and so on. Information from this complex cells are then sent to a hypercomplex cells, which now recognize even more complicated concepts, like what you're seeing is a football versus a volleyball. What you're seeing is a table tennis table versus a dining table, and so on and so forth. So the way the cells in our body are actually recognize final images is there are some simple basic cells which recognize basic concepts, which are connected to more complex cells, which use these basic concepts to build the next level concepts. And there are even more complex cells which take those outputs to connect and create even more complicated concepts. So what you have is hierarchy of cells. Each one of these cells start by recognizing the lowest end, they recognize only simple concepts. Whereas by the time you reach the highest level cells, they are able to take these simple information and are able to recognize more complicated concepts. What computer scientists have done is they have taken this inspiration from biology and are able to construct what are called as neural networks, where you have a mathematical version of a neuron which are connected to other neurons. Therefore, you are creating a network of neurons which hopefully will behave in such a way that the early neurons recognize simple concepts, the next set of neurons recognize more complicated concepts, the third set of neurons recognize even more complicated concepts, and the final neurons recognize whether the pattern that you're seeing is a human face or a cat face or a dog face or a kayak, right? This is what was the hope. This kind of structure they were able to build. Each one of these circles here are called as neurons, and it's nothing but a mathematical transformation. And they are represented by a mix of matrices and nonlinear functions. Okay. And this matrix entries, the weight of this matrix is what tells you exactly what pattern this particular neuron recognizes. Now, I know this is very big, okay? And in a 1 hour lecture, this cannot be made clear as well. But the good thing is we don't really need to understand this in detail in order to actually use it for making for our business code. My goal is to introduce you to the code and show you, even though you might not fully understand what's happening behind, you will still be able to use it to solve a business problem. right? And that is where I'm going to, we are going ahead. And I'm going to now talk some more about how we represent images in the computer in the first place. We represent images as pixels. So we are seeing an image of a person over here. Now we see this as actually a continuous image. But really, this image is represented by pixels. If I zoom into the image, I will actually be able to see the pixels very clearly. A color image like this actually has 3 layers of pixel. A pixel that represents red channel, green channel, and blue channel. 3 separate channels are there. And each pixel value, when I go and look at a particular pixel over there, I would see that pixel actually will have numerical value. A numerical value of 221 representing the blue channel, a numerical value of 210 representing the green channel, and 188 representing the red channel. Right? So every single pixel is actually will have 3 values, one representing each one of those channels. This shouldn't come as a surprise to this audience. I'm hoping that images are represented as pixels, right? When you buy a digital camera and they are talking about the resolution of the camera, what they are talking about is how many pixels does it use to store one particular image, right? So when the number of pixels are large, you're calling that as a high resolution image. Now what we will be doing is we will take these pixels. So let us say this image is a 100 by 100 image, right? So a 100 by 100 image would mean altogether 10,000 pixels. 10,000 pixels, each pixel I said will have 3 values for 3 colors. So that is about 30,000 pixel values. 30,000 numbers would represent this particular image. We are going to take that image, take those 30,000 pixel values and send it into a neural network as input. And what we will do is we will call the output of the image of this neural network and say that this particular image was an image of a person. So this 30,000 values represents a person. Then we will send another 30,000 values of a cat, and we'll say these 30,000 values represent a cat. And another 30,000 values which will represent a dog or whatever, right? We have million images in our training set. Those million images, one at a time, is sent into the neural network. And each time you tag it and you say that this particular 30,000 values, send this. Okay. What they ask the network to do is figure out the weights or the matrix representation of this neuron needs to be figured out in such a way that these 30,000 values, when you input them, matrix multiplication and nonlinear function transformation occur in such a way that the output comes out as a person's face, right? So you figure out these values. Each of these circles represents neurons. It represents a tiny matrix of numbers. The values of those matrix numbers will determine what kind of transformation you do to these 30,000 numbers, so that the final output after doing multiple transformation will say that this is the final neuron will light up corresponding to a person's face. When you send in a dog image with 30,000 pixels corresponding to dog, the final neuron corresponding to the dog face will light up and saying that this is a dog face, right? That is what we design these neural networks to do. Okay, this is a very complicated process of training. We will not talk in detail about what exactly is involved in training, but what we will mention is once the network is trained, what you see is more or less exactly the same thing that animals' visual cortex does. You will find that some neurons respond strongly whenever it notices a diagonal line. Some other neuron will respond strongly whenever it notices a horizontal line somewhere in the picture. And yet another neuron will respond strongly whenever it sees a moving line, whenever it will see an edge in the picture, right? Simple concepts is what this set of neurons will respond to. And these concepts are built in together. And finally, what you would have is one set of neuron which recognizes when it sees when this 30,000 pixels was corresponding to face, then that particular neuron will respond very strongly. And yet another neuron will respond strongly when it actually recognizes a cat, right? This is what a trained neural network finally will look like. What do I mean by a trained neural network? The trained neural network is one where each of these neurons already has its matrix values figured out in such a way that given the original set of pixels, it will light correctly to the final set of the correct light will light up corresponding to whether it's a cat node or whether it's a face node. Now, this training process is a very hard process, and it really requires lots of images to do. When Microsoft trained its ResNet, the training process had to involve it figuring out over 28 million numbers, 28 million values. And the training actually took several weeks of computational time. They required a large supercomputer to actually work through. It was a big computation. To solve. For example, when most of you will have a phone in your hand, which perhaps does facial recognition, right? You point the phone at your face and the phone automatically opens its lock the moment it recognizes your face. How is the phone able to do this? The phone is able to do this because this particular trained network was downloaded into the phone. Your phone manufacturer downloaded it and coded it up right into the chip. And then it takes your image, and that single image, that photo that of yours is taken, and say that I am going to take an existing trained network, and then to that trained network, I'm going to attach one more layer, and I'm going to say that use this trained network, which already has all the basic features to recognize a simple line versus the cat face versus all kinds of things. I'm going to use that network, and I'm going to take the output of network and further add one more layer of neurons, which will tell whether the image that is coming in is not just a human face, but it's a face of Anand or not. Okay. Now, that is all your phone needs to do. The phone needs to identify whether the image that it's being fed in is you or not. So it's actually solving a classification problem. Is this image this thing or not? Now, so the training process, they don't actually train. They don't need a million images of your face to train it. They take a pre-trained network whose values are already determined by million images. And then to that, they just train the last layer of that to identify this specific face. That idea is called as transfer learning. We are already taking a neural network which is already learned, and we are going to transfer that neural network to a new application. That is the idea of transfer learning. What we are going to do is we are going to use transfer learning for the problem that we are going to do. Remember, what does a neural network do? Deep neural network do? The initial layers of the neural network recognizes general concepts, like trying to recognize straight lines versus curved lines. The middle portion of the neural network, or towards the end, it starts to remember class-specific features, whether it's a human face or a cat face. The last layer of neural network, we are going to use it to recognize problem-specific features, whether this is Anand's face or not, whether it is Kamala's face or not, right? The individual person's face or not. That is what we will. That's the way we are going to use these neural networks, because we're already going to get a model that Microsoft has released for free, which has all of these, the first two parts already trained. We just need some small set of images to train this last piece, right? So the recipe to build a super powerful image recognizer is this. We are going to start with the pre-built awesome neural network, the ResNet. To that, we are going to add a last layer where we are going to learn the weights of the specific problem that we are going to choose. Okay, and I'll tell you what is the specific problem we are going to choose in a second. And we are going to adjust the weights of the last layer so that it correctly recognizes the specific problem. Most of the network will still remain as it is with the old weights that Microsoft has already given us. We will just be training only the last layer. And for that, we don't really need a lot of images. We are one step close to moving towards our code. So let me now actually talk about the software that we are going to be using to solve this. Right? There are lots of popular languages that are there in the industry. There are machine learning algorithms available in C++, in Java, in R, in Python. I have underlined Python because Python is what we are going to be using in this demo. Okay, I'm not sure how many people here are familiar with Python, but that's what we are going to use. You don't really need a lot of knowledge of Python in order to understand the code that I'm going to be sharing with you. Because we are not going to write a lot of code in Python, we are going to use a lot of pre-built libraries. Plenty of free pre-built libraries are already available that you can download. One of those libraries is Tensorflow, which is specifically meant for doing AI-based research work. This is given for free. Google created this software called Tensorflow, and it has given it for free. Right? It's all written in Python, but all the complicated math that was required in order to do this pattern recognition and image recognition and all of that is already pre-built in this Tensorflow. And Tensorflow, you know, when it was released just in 2016, early 2016. The technology we are talking about is just 4 years old, right? Facebook did not want to be left behind. Facebook introduced its own version of machine learning libraries, and they call it as Torch. For this demo, we are going to be using Torch. Now, not directly, there are people who took these libraries and to this using these libraries, they wrote wrappers which make it even more easy to use these libraries. There is a wrapper called Keras that's available, which links to TensorFlow. So Keras is something in Python. It's a wrapper in Python, but it uses TensorFlow to actually do the computation. So we are not even going to actually write any code using TensorFlow or Torch. We are actually going to use the wrappers, the pre-written wrappers to actually write code. Keras is the wrapper for TensorFlow, and there is a wrapper called fast.ai, which is available for Torch. And we are going to be using fast.ai for our demo. So enough of talk. Let's go ahead and actually write some code. Okay, let me go ahead to the code screen. And at this point, I would like you to tell me if you are able to see the text on my screen clearly or not.
Yeah, sir, we are seeing it clearly, sir.
Okay, very good.
The letters are clear.
So what I'm going to do is this. Let me walk through the steps that I'm going to do. I believe all of you will have a Google account. And so I'm going to assume that you have a Google account. If not, it's free to go ahead and start it. So go ahead and start, create a Google account. We are going to be doing a problem of image recognition, and we are going to be writing a lot of code. You might say that, you know what, I don't really have a powerful computer. I have an old laptop, which is so good enough for doing these online webinars, but it's really not great for doing computation. You know what? It doesn't matter. We are going to use free resources. We are not going to use your computer. In fact, we are going to use Google's computers, which have powerful machines. And we are going to do all our computation over there. And for this, we are going to need your Google account. Now, there are two basic resources that we are going to use. One is your Google Drive. And I'm logging in to my Google Drive, and I have some folders over here, one folder called Collab Notebooks, and some bunch of files over there, including my daughter's Zoom schedule and so on and so forth. I use Google extensively for a lot of day-to-day activities. I had to clean up this area, this folder, to make it public consumable. But here is what we are going to do. What we are going to do is we are going to write code on Google's cloud servers. For that, you need to go to collab.research.google. Okay. And if you have never gone there before, it might ask you to click accept and sign its terms and conditions and so on. That you are not going to do anything that's going to destroy Google or whatever. But go ahead and click OK in that. And what you have is a place where you can write Python code and experiment and run machine learning algorithms all on Google servers. Now, what we will do at the end of the day today is I will send you this code that I'm going to be showing you. And code and data. What you will do with that code and data is once I send you that code, you'll go to collab.research.google and you will go to the click on file command and you will go to upload notebook. Okay. And when you click on that, you will have to choose the file that I'm going to send you. You can choose, you would have saved it in your desktop. You choose that particular file and you upload it, and it will upload it and it will show you this particular screen. Okay. If it sounds mysterious, that's fine. That's okay. I will share a link which has recorded instructions on what to do and how to do. Okay. So let's not worry too much about it right now. The first thing that I'm going to do now is, so Google directly gives me access into a computer. And if you see in the top corner, it tells me how much RAM is left, how much disk space is left, and so on. Right? Google gives you already some free disk space and RAM for you to go and play. Now, before we start anything, let me first tell you what is the problem that we are going to solve today. The problem that I'm going to solve is doing image recognition. And I am going to, I'll tell you what I did, and I'm going to, so I went to google.com and search for, say, temples. And I clicked on images. Now I have images of these different temples. I saved all of them. Then I went there and typed churches. I got different images of churches. I saved all of them and went ahead and typed mosques, and I got different images of mosques. I saved all of them, and all of the saved images I saved in my Google Drive in a directory called worship. Okay. And inside worship, I created a directory called train, and there I stored these images. Okay. There is a directory called models, which we don't need. I'm going to delete it right now. These are the ones. So if I click on the temple folder, these are all the saved picture of temple from Google. Okay, different types of temples. And same thing over here, different pictures of mosques. And so on and so forth. Now my goal is this. I am going to, now the ResNet, the algorithm that we are going to be downloading from Microsoft, does not actually know about Indian temples or mosques or churches, right? What we are going to do is we are going to take ResNet and train an algorithm which will be able to correctly detect whether the picture we are seeing is a temple or a mosque or a church. That is our business problem. Okay. So, and if you see the pictures, there is really a wide variety of temples. I mean, how would you describe a temple? Well, if I need to tell that my daughter, say there's a tower in front of a typical Indian temple, Gopuram is there. But what is considered as a Gopuram is tricky. This is that lotus temple, right? But that's a temple, and there are these bunch of other old temples that are there. And did I see a face in one of them? Yeah, there's all kinds of temples that are there, and some of them are interior of a temple, right? So we don't even have a reference Gopuram to try and detect it. And the same thing is kinds of complicated images are there with churches and mosques as well, right? If I scroll through the church image, some of them are interiors of the churches, which as human being, we know, immediately we know. But how will the image know? How will the computer know, right? What is the pattern it's actually recognizing? What pattern should I code in for it? If I have to take a rules-based approach, it's almost impossible for me to create a set of rules which will correctly recognize all of the images, or forget even all of the images. Even half of the images correctly recognizing is a big challenge, right? How do we do that is a question. So that is the business problem that we are going to try and solve. Given the set of images of temple, mosque, and church, we are going to train an algorithm which will correctly recognize this. So for that, I am going to use the fast.ai's wrapper. And this first line of code, what it does is it downloads the wrapper information from the fast.ai's website and sets it up on your computer. Okay, you click play on that. It essentially connects to that this thing and it updates fast.ai. It's done. Okay, and then I'm going to import fast.ai. It has just downloaded this. I need to import that library into my current memory. The way Python works is that Python has really thousands of libraries that are written in that are publicly available. You might have downloaded a particular library, but it's waste of memory to store in your memory all those 1,000 libraries. So what we do in Python is only when you need a library, do you import that particular library into the memory. And so here, this particular command, I'm importing the fast.ai's vision related libraries. So from fast.ai.vision, import everything. That is what this command is saying. Now, it might give you a bunch of warnings, and I'm going to ask it to ignore all the warnings for now, which is why I'm putting this thing. This is really not good coding practice to ignore warnings, but it's going to make our interface look crazy. So for now, I'm just going to say ignore all of those warnings. Right? I move on to the next code cell. This code cell is basically saying, I'm using the Google Colab. Google Colab is this environment where all of this code is running. And Google has provided its own set of libraries which are preloaded. And that is this library called Google.Colab. From Colab's library, I want to import the ability to connect to my Google Drive. Why do I want to connect to my Google Drive? Because Google Drive is where I've stored all of these images. All of these images are stored there. So I want to go ahead and connect to my Google Drive. So I import the library to connect to Google Drive, and this drive.mount actually connects to my Google Drive. Okay. Now Google will first ask for authorization. It will show you this, that go and click to this link in the browser. You go ahead and click in this browser. It will give you a code. It'll ask you, are you authorizing it? You say, yes, I'm authorizing it. Then you take the code and you paste it, the code here, and it will automatically mount it. So your Google Drive becomes like another mounted drive in your Colab. Are we all with me right now? Any questions? This is important. So it's important that if you have questions, you ask them. Share the code. Yes, I will be sharing the code once the session is done. We will be sharing the code. But I don't see any specific questions right now. So I'm going to move forward. Uday, that's a good question. Those companies could have earned so much money from the algorithm. So why did they release in the open? That's a very interesting philosophical discussion. We will see. If we have time, we will talk about it. Right? I enjoy those discussions. Unfortunately, today we are going to do this in today. This portion of the is important for me to go through the code. So I'm going to go through the code. Okay. We have not stored images in D images. We have stored it in the Google Drive. So it's on my drive, and then in the directory called ML. In ML, I have a directory called hands-on, and in hands-on, there is a directory called worship. And in worship, there is a directory called train, and that is where all the images are stored. Okay. So what I am doing is I have first imported the Google Drive, and then I'm going to set the path. I'm going to CD, change the directory to from the base Google Drive area. I go to my drive, ML, hands-on, worship. Okay, I did a CD to that. And then I'm going to set the path to train, because it's in train that I have these three directory of images: church, mosque, and temple. All those three are there. So I I'm storing that three directory of this thing. And then I did ls of path. What is path? Path is the train directory. Rene is asking, we have already logged into Google account, but why do we need to mount the drive? That's a very good question. It's a security issue. Now, any program, you might have accidentally downloaded some Python code from the web, and you go ahead and execute it. That program will have access to your Google Drive. You don't want that to happen. So what Google has done is they actually are allowing you, asking you to explicitly give permission. Does this Python code have access? Should this Python code have access to Google Drive or not? Right? And so that is why you need to go ahead and enter the authorization code and all of that, and then you mount this Google Drive. Okay. We will mount the Google Drive, and here this process of mounting a drive and all that, if it sounds strange to you, that's okay. It's just a technical detail. But anyone who's worked with a Linux system will know this idea of mounting a drive and unmounting a drive. For Windows users, when you plug in your USB drive, Windows automatically mounts the USB drive, and you have to eject the drive, right? The ejecting part, Windows forces you to do. But when you're using a Unix system, you need to explicitly mount a drive and unmount a drive after you're using. This is your Unix system, and that is why this mount and unmount command is coming in, right? But if it is complicated, forget it. Don't worry about it. You have this code. You will be able to explicitly play with the code. And the only way you learn programming is by getting your hands dirty. You actually go ahead and play with the code. You will learn it, right? Programming is really not an observational sport. You need to get in and play with it. And you will be able to play with it tonight, because I'm going to be sending you this code and all these images, location where all of these images can be downloaded. As a start, download these images and copy them into a Google Drive. And then you can start using this code as it is, right? Now, I see that in my path, I didn't execute it before. And let's see if I execute it now, what happens. It's saying that church, mosque, and temple are the three directories that are there in my directory, right? Then I say that I am going to create a machine learning algorithm which needs to detect three different categories. It's going to be either a church, mosque, or a temple. Okay, so I say that this is the list of classes, final classes that I have. Okay, and I am going to, the next set of code is this. Okay, this is a list. Okay, it's an array or a list that is there in any other programming language, right? So I'm writing, look at this command. For every entry in this list, go ahead in the path, where is the path defined? Path is this train directory, right? Go ahead in that path and look for a directory named this entry C, right? So path underscore C is saying that go to the train directory, and in the train directory, look in the church directory. Then you look in the mosque directory, then temple, each one of them, right? You go into each one of them and you verify images in that. Check if there are any corrupt images. If there are corrupt images, you delete them. That is what this command is there. And max size is 500. I'm saying if there is more than 500 images, delete the rest. I want only 500 images for training in each class. So each of these classes will have at most 500 images. When I click on that, it will go ahead and download, check the chart, this thing, each one of the directory, it goes ahead and checks all of them, right? Then these images needs to be loaded into the memory. This step only involved verifying whether it was a corrupted image or a good image. Now I need to load it into my memory before I send it to my machine learning algorithm for training. So I have this next one line code, which is going to do a whole bunch of activities. Here is this long one line code. Let me go through it one step at a time. Okay. This is the beauty of working with FastStart.ai, right? The task that we have done till now would have required a minimum of 150 lines of basic Python code. Now we have done this in basically simple 8 lines of code. Now this line of code by itself underneath would probably represents 400, 500 different lines of Python code. They have all bunched it up together in one line of code. Let me start by talking what it is. First, I want to read all of these memories and store it in a structure. Many of you are from a computer science background, so you understand what a structure means. There are different kinds of structure. List is a type of a structure, right? This structure in FastStart.ai is called as image data bunch. So imagine this as a list of actual image information. Okay, it's you're saving it as a effectively like a list. In this case, it's not called a list, it's called as an image data bunch. Okay, so I'm asking it to build an image data bunch by reading it from a folder. Oh, this is another cool thing, right? When you work with this interface, you can just hover your mouse over the any command and it will tell you what it's actually doing. It's actually saying this is a data bunch. It's going to create a data bunch suitable for computer vision problems, right? So help is also available right there when you don't know what the particular image is. Now, I'm going to say create a data bunch from information in the folder. Okay, I'm going to give in the argument what folder is it. Well, the folder is available in the path. Path is a variable I mentioned Ariel before. I defined it here before. Okay, and to train the computer network, I am going to use all the images in the path. So dot represents current directory. In this path directory, you use all the images. Okay. Convert those images to the size of 224 by 224 pixels. Each one of the image that is there might be of different pixel size. So when I look at this image information, let me see details. This is 319 by 158 size image, right? So each image will be of a different size, but all of these algorithms require the image to be of the exact same size. So we are going to say, take that image, resize it to a size of 224 by 224. Okay, so this is because this once you have all the images to be the same size, because you want your algorithm to recognize features in the image, not necessarily the size. So as long as the size is not too small, it's okay. So we have the Imagenet algorithm was trained with 224 size image. So we are going to make sure all of our images are of 224 by 224 pixels. That's the goal. And this we are saying reduce all the images to size 224 by 224. Number of workers is 4. So I'm actually going to ask you to use 4 cores to do this. Okay, you typically get a multi-core machine. I'm going to use 4 different cores to this thing, because since multiple images are going to be loaded, you don't need to load them sequentially. Let each one of the cores separately load the images and add it all into this image data punch. Right? Why size 224? Because the original Imagenet was created with size 224 by 224 images. So we want to make sure, since we are feeding into the image ResNet image, we are going to create into the same size of 224. That is why. Then the thing is, once I get the image, the algorithm will go ahead and try to learn what is the details in the image. We are going to also say the label that this image is a temple, this image is a mosque, this image is a church, right? It will go ahead and try to learn all of this information from the images, and but it might be end up doing is it might just memorize the images. Instead of learning general patterns, it might just memorize all of the images, and we don't want it to memorize. I want to be able to show to the computer another image of another temple taken from a different angle, and I want it to still recognize it's a temple. So I wanted to learn, I don't want it to memorize, but I wanted to learn important features from the images. So in order to check whether it is going to learn important features or is it just purely memorizing or not, what we do is we create something called as a validation set. Validation set is basically, we are going to take 20% of the original images. Okay, if I have, let us say 1,000 images, I'm going to take 20% of it, 200 images. 200 images I'm going to set aside. I'm not going to feed it into the computer right now. But when the training process is happening, then the training process is happening, it will go ahead, learn while training, it'll check on these 200 images and check whether these 200 images which I haven't seen till now, am I able to correctly predict it or not? So I'll be able to validate whether my learning is happening or not. It is like me giving a lecture and giving you a quiz every now and then to validate whether you have actually learned it correctly or not. By the amount of correct answers that's coming from the validation, I will know how well you have learned that particular topic, right? So for the algorithm, we are going to set aside 20% as a validation data set, right? And then there is this part called transformations. Get transformations. What is that? When I take an image, I want to take the image and learn from it all important features, and not just details that there is an eye that is there in the 3rd pixel, or whiskers that is there in the 30th pixel, or something like that. I don't want to learn that. I wanted to learn generalities. So instead, what I'm going to do is I'm going to take an image. So for example, I can take one of the image, like an image of a bird, and then I am going to create multiple transformations out of the same image. Some of them zoomed in, some of them at tilted angles, some of them with color changes, some of them with angle flipped. All kinds of transformation of that images I will do, and say that all of these are also birds. This one alone is not a bird. Any image which has come under any of these transformation, all of them are also birds, right? That is what I wanted to learn. Similarly, when I'm going to here feed in pictures of temple, I want to take the original image and feed in transformation of temple pictures and transformation of mosque pictures, transformation of church pictures as well. And so for every single image, it is going to create 1,000 new transformed images. Every single picture of a temple it's going to take, it is going to zoom in a little bit, it's going to unzoom a little bit, it's going to tilt it a little bit, it's going to change the color a little bit, and then say all of these are still temples, right? And that way, the training algorithm has even more amount of images to train. And that is what we are going to do. Once I do this, it will load up all of these images, and it's done. I can check the batch statistics. And what does it say? It has there are from category list mosque, it loaded 480 items. Each one of the item was 224 by 224 images with 3 color layers. Okay, these each one of these images, it's loaded 481 of mosque category, 120 different 480 of altogether all categories, 120 we are going to keep it as our validation set. Okay, these are the images that it has loaded. I can go ahead and ask it to randomly pick some of the images and show it to me. Okay, I'm saying here, show randomly in a 3x3 batch different images you have loaded till now. So it says, it shows some examples of images it loaded. This is a temple image it loaded, temple. This is a church image it loaded. This was a mosque image it loaded. A bunch of them it had loaded. Now here comes the best part. Over here, I am loading in. Here is where I'm going to say, download the Microsoft's algorithm, the ResNet algorithm, this masterpiece of an algorithm which had all the pre-trained weights that beat the expert human level accuracy. This single one-line command downloads that algorithm from the web. It's a 97 MB file. It goes ahead and downloads it. And now you're ready to train. This command, next command, is learn.fit.onCycle. I'm asking you to train this this existing algorithm, but train it with these images that I have downloaded, right? And that is what it does here. This following set of steps is basically training the algorithm for that. It starts out, since it's already a pre-trained algorithm, it starts out already with 90% accuracy. Of all the images that you have, it already has a 90% accuracy in the validation set, in the unseen data. And then one at a time, and as to every training cycle it finishes, it keeps improving the accuracy marginally. And by the time the training is done, and it is already at 92% accuracy, 0.92 is 92% accuracy, right? Fantastic percentage of accuracy already. And I haven't used 1 paisa of my computing time. I have used entirely Google's free account to do all of this so far. Now what I can do, I can go ahead and interpret the result once it has learned. Okay, this is a command that allows you to do the interpretation. What does it do? It looks at the 20% of the images that you set aside, the validation set. And it's trying to figure out how many of this did you get it correct and how many of them did you get it wrong. This 20% items that you separately stored, right? How many of them did you get it right and how many of them you got it wrong? That is what this command does. Classification interpretation. And I'm asking it to plot the interpretation. It plots the interpretation. This kind of plot is called as a confusion matrix. How do you interpret this plot? It says in the validation image, there were actually 35 of church images which were correctly interpreted as church. There were 0 of church images which were interpreted as mosques. There was 1 church image which was interpreted as temple. So this is the items that are there on the diagonal represent your correct interpretations. The items that are there on the off diagonal represent your wrong identification. So for example, there were 3 temple images which were actually identified as church. There was 1 temple image which was identified as mosque. And there were 37 temple images which were correctly identified as temple. Right? So that is the confusion matrix. It tells you which are the ones that got wrong. We will be able to look through this and find out exactly which was the image it misinterpreted and try to understand a way to improve the algorithm. Now, I see one question saying that, why did I train the algorithm for 10 cycles? Okay, this you can train the algorithm for 100 cycles if you want, but sometimes what happens, when you train it more and more, it starts to memorize data instead of figuring out broad patterns. right? But typically, most of the problems you do, 10 to 15 cycles are good enough of training. Okay, because we are already starting with a state of the art, well-trained algorithm, and we are just going to train the last layer of the algorithm to do this, and it goes ahead and is able to create this confusion matrix. And I can actually view in this confusion matrix, using this command called class confusion, and I can actually check which of the images were wrongly identified. And you know what it says? It says a bunch of these images were wrongly identified. This picture of a temple, it looked at it and it recognized it as a church. It made a mistake. I don't understand why it made this mistake, but this was the mistake it made. The second one is a mosque picture, which recognized was a church. Let's look at it. This is actually a picture of a mosque, but it recognized it as a church. And I can sort of see why, because, you know, it's got these angles, these sharp angles. Sharp angles are typically we see in churches, not in mosques. So it recognized this mosque as a church. And then there was this mosque that was recognized as a temple. Let's see what that image is. Oh, this is a mosque. It recognizes a temple. You can look at it and you can see why it recognizes a temple, right? It sort of thought that this is a gopuram. And that is the reason it went ahead and recognized this as a temple. So even when it makes an error, you can look at it and you can figure out why this error was there and then decide, does the training need further refinement or not? Okay. All of this I was able to do with just how many lines of code? I have what? 8 steps. So altogether, maybe 10 lines of code. And anytime I download a new image, I can send it, use this existing algorithm to train it and ask it to predict. And last here is where I'm doing. Using the learned algorithm, predict for this new image and tell me what this is. For this new image, it went ahead and predicted and said it's a temple, right? We are able to accomplish all of this with basically about 10, 12 lines of code, because we are starting off with a pre-trained algorithm. This pre-trained algorithm, which took several weeks and multiple PhD researchers to create, right? Microsoft has given it for free and we are able to download and we are able to build all of this. Now this, of course, what I've done for you, what I've shown you here is a toy problem. It's a business problem, right? Well, even this toy problem is actually useful, right? Google uses this kind of algorithm to actually do this image searches. Right? How did Google find all of the images of churches? It used this algorithm to figure out all of this thing. So Google has its version of this inside. But can we as users use it for some other business purpose? Yes, we can use it for a business purpose. I know I have 3 minutes only official time left, but I urge you to just give me a few more minutes. Just a few more minutes. I am going to show you another example. If this didn't blow your mind, that absolutely will. Here's an example where I was able to download use exactly same piece of code, right? Exactly same piece of code, but for a completely different problem. You know what the problem is? Let me go back to my drive, my ML hands-on, and here is a directory called COVID. I was able to get access to X-rays of patients, normal patients' X-ray files, the chest X-ray of normal patients, and chest X-ray of patients who have had seasonal flu. Okay, are you able to tell the difference between them? I cannot. I'm not able to tell what is flu X-ray versus what is a regular X-ray. And there is a COVID, and here are X-ray of COVID patients. And again, I am personally not a radiologist, and there is no way I can tell what is looking at X-ray, whether this person has a normal X-ray, flu, or is it COVID. I won't be able to even say this. But you know what? This particular code, this exact code that I used before for recognizing whether something is a temple or this thing, same code I'm going to use. Instead, now I'm going to point to the COVID-19 directory. Instead of the worship directory, I'm pointing to COVID-19 directory. And I am going to say now the 3 classes are not temple, mosque, and church. Instead, it is COVID, normal, and seasonal flu. And it goes ahead and downloads all of those X-rays and says this is a seasonal flu X-ray and all that. We had already labeled it, right? We labeled all of this. We ran the same algorithm, and this algorithm now starts off with 30% accuracy. Why did it start off with such low accuracy? Because the Imagenet algorithm did not have any X-rays when it was trained. It was trained on pictures from the web. It was not trained on the web, on the X-ray pictures. So it originally starts off with 30% accuracy, but I trained it for 15 cycles instead of 10. You know what? Slowly the accuracy improves. By the time we get to the end, it already has 92% accuracies. I bet you 92% accuracy is better than an average radiologist that you have working in a hospital. This algorithm, which did not require a medically trained expert to write, which was an algorithm which was trained on cats and dog images, is now able to identify with 92% accuracy whether someone has COVID or someone has seasonal flu or they have normal result. And with what? 10 lines of code. And I was able to do all of this and finally able to recognize which are the ones that are wrongly categorized, and given one final X-ray, tell whether this particular person actually had COVID or is it a normal X-ray. Pretty amazing, right? Remarkable that you're actually able to do all of this with this kind of ease. And this is the reason why there is so much hype about data science. And actually, in my opinion, it's not hype, right? If I, as a regular practitioner, am I able to download this information and actually make progress on current research work, right? And I'm able to contribute. That's telling you that what I have is tools which have of amazing power is being given access to me. And now I can make contribution. I am right now working on a consulting project with a US-based pharmaceutical company for their COVID project. I'm not a medical person. I have a PhD in physics, right? And I'm making progress in this particular project because I have data science and I have these tools and understand math. And using math, I'm able to do all of this. And you will be able to do this exact thing by this evening when I share with you this code by the end of the day. Thank you so much for paying attention. Let me just make one final slide. It's my responsibility to say this. If you are really interested in learning more about this, the place that I teach is called as INSOFI, which stands for International School of Engineering. They are offering a free course that's happening right now. Once a week, there is a lecture, 1 hour lecture, 20 lectures. That's free. All you need to do is go log into INSOFI and search for the term real world data science. And 2 lectures are done. And this material that I covered today is basically those material that was there. But there are still 18 more lectures that are left. If you're interested in learning more, you should go and register for that. Thank you so much for your attention. I'm happy to address any questions that are there.
Thank you. Thank you very much, sir. It's very, very informative session. Awesome. And a few standard questions I would like to ask you, sir. First
Sure.
one, just a minute, sir. Just preliminary questions only. First one, why we should fix? You are fixing that size as 224. It's for compactness or any other reason, sir?
Yeah. So the original ResNet that we are downloading for from Microsoft, that was trained on images of size 224 by 224. Okay. And that is why. So this challenge, this Imagenet challenge that I talked about, all of the images were scaled to 224 by 224. Okay. And so the network was trained for that. And that is exactly why we are scaling our images also to 224 by 224, and we are using this.
Thank you, sir. And the second one is, so you have said to 80% of training set and 20% for testing. Is it the standard size, sir? As per Handcamber, they have given 66% and 33%. Is there any
different? There is this is entirely personal choice, and different people use different numbers for that. I generally use 80-20 or 75-25. I like more of this information to be there in training set rather than in test, but it's personal choice, really.
Okay. Yeah, normally in PhD Viva, we used to ask these questions: where you get this number? Whether have you referred any paper, research paper or something? So
yeah. So this very much depends on the kind of problem you are dealing with. The problem, when it doesn't have too much data already, you want to use as much data as possible for the training. When you have plenty of data, you might even be using only 10%. So for example, right now when Google in their image recognition algorithms, they cannot afford to train the network on all the images that they have. They probably use only 10% of the images that they have to train the network. So it really depends on the situation, and there is no yeah, exactly.
And 10 cycles and 15 cycles. So this is also on trial and error basis, sir.
Exactly.
Also, we used to give this number of cycles.
Correct. So these are called as epochs. I haven't defined what an epoch is and all that. These are things that they will learn when they actually learn some ML. They will understand what is overfitting, what is underfitting, and why you might end up overfitting when you train for too long. And those kinds of details are all there. And there is a way to control overfitting, but I didn't want to overload them too much. And
Yes, sir. Yeah, it's thank you, sir. Thank you very much. It's a very, very informative session, sir. Even we enjoyed this session. Thank you
so much. I can stick around for 2-3 minutes if there is any questions from students. Otherwise,
actually, they have asked this related to these only cycles, percentage of training test data.
And wonderful.
They have asked to share the code.
I will email the link to my Google Drive, and I'll be able to do that. But the thing is, if they are able to register in this course, it's done by a different professor, an excellent teacher, Dr. Dakshinamurthy. The video for the 2 classes, sorry. The video for this, even though 2 missed lectures are also freely available. Not just that, the code that I've used, all of them is also freely available. All of that is available over there as well.
Okay. Sir, another question is, why num workers is equal to 4?
So this, it depends on the machine that is available for your training. So Google by default, the training, this thing that they allocate to you is not super powerful machine, and hence it has only 4 cores. But I will be able to request Google the use of GPU as well, and that has actually really large number of computing power as well. And so Google allows you to play with all of this up to some point. When you start enjoying it, and when you start using it more, that is when they start charging. But it's a wonderful resource for students to learn, because you can go for free without trying hard to set up Python on your notebook, figuring. Wow, there's feedback. Yeah. So without setting up, struggling to set up the software on your machine, you can just use the Collab and start working on it for free.
Is the procedure same for text also?
So text, what we are using here, let me show you the place where we are downloading the model. This model that I'm using is a ResNet model. This is only for image. And we are talking about CNN. CNN stands for Convolutional Neural Network. It's only for images. For text, there are different kinds of models. It's called LSTM is one of the popular ones. And that's where details get in. But you know what? For now, I won't want a beginner to worry too much about this. I want a beginner to just admire at how easy it is to start playing with it. The students of this course can go ahead and download from Google their own set of 3 categories of images and try to see which one works. For example, you can try downloading dogs, cats, and zebra, perhaps, or you can try downloading Surya, Vijay, and someone else, and see if it's able to recognize it, right? This is the way you learn, by trying to download images and and the same code will flow through. No changes will be needed, and you will be able to do all of this.
Thank you.
Okay, thank you so much. It's been an honor to be talking to you all. If any feedback is there, I would, if you can email me that, then I'll very much appreciate
Thank you,
that.
sir. Definitely, sir. Thank you, sir. Thank you very much for this wonderful session.
Thank you, ma'am.
Okay, participants, you can post your feedback in the link given in the chat box. Okay. Time ஆயிடுச்சு. Thank பண்ணிட்டேன். Thank you, sir.